Well, welcome back to part 3 of our Getting Started with Easy5 for Adams users. In the previous 2 videos, we covered quite a bit of ground in terms of what is Easy5. We spent most of our time looking at how to model the simple mass spring damper system in various ways in Easy5, eventually coupling it to Adams in co-simulation mode. In the second video, we then looked at adding friction and bump stops both to the Easy5 spring mass damper component as well as to Adams, and saw that we got almost identical results in doing that. And so everything has worked well so far. The last step in the process now is to actually add a control system to our Adams model. So we have a mass spring damper system which we want to be able to control in order to move the mass to a very specific location. And so just one slide here which talks a little bit about control systems. If you recall from your control system courses at university, you will hopefully remember that to control something, you need to have a set point or a desired signal coming into the system. This then goes through a controller, and I'll talk about this in a second. The controller then generates a force which gets fed into your system model. And here you'll see this is in the transfer function form. So there's a force that goes into a plant or a process, and that generates a certain output. The output then is fed back, so that's why it's called a feedback control system. It's fed back and compared with the desired signal. And so the desired signal minus the actual output of the plant generates an error. And it's that error that we then use in our controller. And the most common and widely used form of a controller is called a PID controller. That stands for proportional, integral, and derivative components. And so basically what that means is we take the error signal and we simply apply a proportional gain to the error. So that's one aspect of our controller, is to take the error, multiply it by some Kp value, and we get part of the force that we're going to feed into the plant. The second aspect is the integral component, which basically takes the error and integrates it over time, and that's also multiplied by a gain, and that's fed into the force function. And then the derivative component basically takes the derivative of the error, so this is picking up on how quickly the error is changing, and then multiplying that by the KD gain, and that then gets summed together with the proportional and the integral gain or components, and that generates a force function. That force function is then fed into our plant or our process, and that generates a response. So this is generic in terms of control systems. We're going to now look at 2 ways to do this in Easy5, and I've specifically chosen quite a difficult input signal, which is a sawtooth signal, which has got sharp corners, and we know that it's going to be very difficult for our mass spring damper system to follow a desired sawtooth pattern, but we want to be able to test our system. So with that, let's move over to Easy5 and to talk through this model. So there's that diagram that I've kind of just discussed with you, just a slightly different picture of it. Our set point gets fed, the error set point gets subtracted, the response of the plant gets subtracted from the set point, that generates an error, goes into our controller, that gets fed back into the plant. So what I'm going to show you here is there's our Adams model. We'll come back to that in a minute. But what I've done here is I've effectively taken this control system diagram, block diagram, and I've created a PID subsystem model in Easy5. So if I double click on that, you'll remember from the first video, we simply just dragged all the various components onto the canvas. And so here I've got my summing junction, I've got my proportional gain, I've got an integrator with the Ki gain, the integral gain, and then I've got a derivative block which differentiates the error signal multiplied by the KD gain. These three values then get summed together and get passed out of this submodel, and what comes back into the submodel is the displacement of the mass. So the displacement of the mass gets compared with the desired position of the mass, and that generates the error. So if we go back up one level, you'll see the connection. So the force that the controller generates out is fed into Adams. Adams then processes that force and sends back the actual position of the mass, and that allows the controller to do its work. And the controller is getting its command from this triangular wave generator, which is giving us the desired position. So that's one submodel. On the other end, I'm showing you that Easy5 also has a PID control component, which takes this entire submodel with all these different blocks and simply does it all for you in one single PID controller. And so if I double click on this, you'll see we have a simple option to be able to put in our proportional gain, our integral gain, and our derivative gain, and the rest is done for us. And so what you will notice here is I've created three variables, KP, KI, and KD. And so as I change these variables to try and tune my control system, these variables are fed both into this submodel, KP, KI, and KD, and it's being fed at the same time into my PID controller. So this shows very easily how I can change the variables, and two parts of my model are being updated automatically. So this PID controller then generates an output signal, which goes into what? It goes into our mass spring damper submodel, which is simply the orange block that you'll recall from the first video when we modeled the actual equations of motion for the mass spring damper system. So all I did, and that's what I wanted to just show you here, is when you've got any sort of group of components that behave together as a submodel, you can simply drag a window around them and right click and say create a submodel. And so you can create multiple layers of submodels within submodels in order to simplify your system analysis. And so this is just a way to now compare the same PID controller, one built by hand and one using the Easy5 component, one fed into the linear mathematical model and one being fed into our final Adams model. So if I double click here, I simply select and configure again, and I pick the final model we exported from Adams previously, which included both friction and the 3D contact for the bump stops. And so this model it has all the nonlinearities in, whereas this other submodel does not. And so that's all we need to do for that. And so the goal here is just to quickly show you how the PID controller will try and move the mass according to the desired sawtooth pattern. Now, to make things worse, I've specifically told the sawtooth to move from minus 0.3 meters to plus 0.3 meters. And this is going to be a problem because the bump stops are going to activate at 25 centimeters, and so the control system won't be able to follow it all the way. And so let's have a look and see what happens. All right, just before we start the simulation, there's one more thing that I need to just mention, and that is that when the sawtooth generator starts, it starts with an input signal of minus 0.3, but the Adams model is currently sitting at a position of 0. And so the error is going to be massive. The force that it's generated is going to be massive. So we need to create an initial smoothing function to kind of smooth the Adams model in so that it doesn't obviously explode right at the beginning of the simulation. So to do that, I'm simply going to bring up my Adams model, and we're going to go into our force function, modify the force function, which is being driven by the F external parameter coming from Easy5, and we're simply going to multiply this with a step function up front. I'm going to say step, and let's just put enter there, so I'm going to say step time, and for at 0 it will be 0, and at 1 second it will be a value of 1 multiplied by the variable that Easy5 is written. For the first second of the simulation, Adams is going to basically just gradually ramp up the signal for us, and then it will follow for the rest of the simulation simply 1 times whatever value Easy5 feeds through. So we've made a change to the Adams model, so that requires that we do a plant export again. Quickly do that, and now we're ready to go back to Easy5 model. Alright, so now we are ready to run the simulation, so we're going to run it for 10 seconds. So remember the mathematical model, it's got no smoothing function up front, so it's going to try and follow this Sawtooth pattern as it is given. The Adams model has got the smoothing function for the first second built in. So we press run and we just wait for Adams to fire up. Alright, so there's the Adams model, and here's our strip chart. You can see that the blue line is the displacement of the mass without friction and bump stops. The yellow line is the output of the Adams model, which includes both friction and the bump stops. Right, so I think that's run for long enough, so we can stop the simulation and then move over to the plotting window. And there we see the desired position. So that's the Sawtooth function generator that's trying to move the mass from minus 0.3 to plus 0.3 in a Sawtooth pattern. This is the response of the mathematical model of the mass spring damper system. So it'll be good to plot them on top of each other. So let's go to the desired position, and then we will add to this a new curve, which will be the mass displacement. All right, and let's make that red and a little bit thicker, and then let's add another new curve, which will be the Adams results, and so that's mass dx, and we can make this perhaps green and also a bit thicker. All right, and so there we can see the underlying desired pattern that we wanted, and the red graph is how well the mathematical model was able to follow, and you notice it actually has quite a far overshoot. So the force is pushing it towards this, but then it overshoots and it has to pull it back. The Adams model, however, hits the bump stop and so stops short, and once again you can see the Adams little contact spike where it has to first penetrate and then it gets pushed back onto the 25 centimeter bump stop line. And so there we've very simply, using two different methods, both the mathematical model and the Adams model, we've been able to generate a very simple PID control system that gets our system to follow the desired input value. And then from here you can go on and tweak these parameters, push the gains up and down, and see what kind of response you get from the system until it is within the desired performance that you would be happy with. One last interesting result that we find from this simulation is what the force looks like that our PID controller is generating. And so if I select the PID force out, what you will notice here is that the force value has these spikes every time the mass hits the bump stop. And what this simply is that the controller is trying to move the mass to a position of 0.3 meters, but the bump stop kicks in at 0.25, and so the force ramps up to try and move the block in that direction, but it can't because it's hit the bump stop, and so you get these very high spikes. And so again, from a loads or an FEA perspective in terms of stresses that the model would be subjected to, you might need to figure out a way in which to limit this force spike from occurring, so that you don't obviously put your system under too much stress. So again, a connection then to further analysis that might be done with NASGAN or MARC, or some tweaking on the control system might be necessary to prevent these force spikes from occurring when the mass hits the bump stop. Well, that then brings us to the end of part 3 of this Getting Started with Easy5 for Atoms users video series. Thank you for watching. I hope that you found it interesting and that you are eager to give Easy5 a try. I know that there are many applications that I haven't even been able to touch on, and hopefully you'll explore that with the team at Simteq. I would love to help you investigate how you can use Easy5 in your engineering, design and simulation process. There will be one more video coming out in the series soon, and that is to show us how we can connect Easy5 and Atoms to external hardware like an Arduino, where we can actually integrate external force transducers or pressure transducers connected to an Arduino, feed that signal into Easy5 and pass it across to Atoms, so that you're actually able to physically interact with your atom simulation model while it is running. And so that's just one new avenue that we are looking to explore, and look forward to seeing you with that video soon. Thanks for watching, and look forward to making contact with you as you explore Easy5 further. Goodbye.